Okay, this is section 3.1 continued, and we are on page 103. So if you're not there, all you people out here, get there, please. Page 103 is just a couple more examples, but they're pretty important. What the heck, yes, what?
We thought we were supposed to, we thought this was due today.
Oh, no, we didn't get to finish the lecture, otherwise it wouldn't be.
Okay.
Okay, so we were on page 103 when we were interrupted because they shortened periods on Thursday, and I thought I had more time, and we don't, so anyway. What I was telling you was, if you'll recall from the end of the last one, is the title of your book, Graphical, Numerical, Algebraic. We have seen examples so far. If you'll just to remind you what's going on, we've seen the algebraic method. We saw that in example 1. We've seen that many times already. We saw a new version of the derivative and did some algebra on that. Worked out nicely with radicals. That was a good way to do it by rationalizing the numerator. We did a graphical example by looking at example 3 and talking about perhaps having the context being the depth of water in a ditch over several days, and how we compare the actual function to its derivative as a graphical thing. We also looked at different notation. We actually took a derivative graph and determined what the original graph looked like from it. That's the one you had covered up with a little post-it in the column on page 102. And now we are on page 103, and the one thing that we have not looked at yet is the numerical representation of a function. And numerical, when you see that, you need to start associating that word with tabular information. It's got a table associated with it. A bunch of individual spots on a graph that, if you connected with a smooth curve, would represent continuity. And so example 5 is a sample of that. Now, having shown people this example many, many, many times in calculus classes, everybody seems to get hung up on the probability experiment. And I need you to be able to set that aside. If you were in a statistics class, you would work out these probabilities. But you are not. You're in a calculus class, so stop it. This is what I mean. It says, suppose 30 people are in a room. What's the probability that 2 of them share the same birthday, ignoring the year of birth? It means just the same day of the year. That's a very intriguing thing. Very interesting. However, we are not here to try to figure out how they figure those probabilities. You're going to take this as a numerical or tabular representation of a function. It's given to you in a table as a function. But you must think of it as a function. And here's what it says. What?
We don't get to find out how it happened.
I'll tell you in a stats class. Go Google it. It's all over the place. People are always intrigued by it. You figure it out on your own. We're just going to take the numbers as facts, okay? Just before we go on from that, though, there are 10 of us right now in this room. And I'm going to tell you my birthday, and I want to see if anybody else in here has it. We're going to go through, and if you hear someone say your birthday, then speak up. We'll see if we're all unique or not. I'm October 6th.
February 2nd. 25th.
July 12th.
June 28th.
January 23rd.
June 24th.
September 30th. July 6th. September 13th.
See? At least in a group of 10, everybody has a unique birthday. Look at the probability. If there are 10 in a room, the probability that 2 of them have the same birthday. What is it? Pretty small.
10.
About 11, about 12% chance that that could happen in a group of 10 random people.
That's so pretty good.
Yeah, it's still pretty good odds, but we didn't meet that. I mean, there was an 88% chance that it wouldn't happen, so we fell to the side of probability. But anyway, notice that after you get 30 people, it's better than half. When you get to 60 people, it's practically assured, 99.4%, with only 60 people, and yet there are 365 days in the year. This is an intriguing thing. When you get to 70 people, it's pretty much assured. How many people would you have to have, just for the fun of it, how many people would you have to be absolutely certain that 2 people had the same birthday?
366.
Come on,
367.
but it's almost certain with only 70.
Wait, no, you have that 367, because we think February 29th.
Yeah.
That's 366.
Yeah, so, like,
To guarantee
Yeah.
anything.
yeah, because you'll need,
So
everybody's,
leap year is 366 days.
Yeah.
So you need
So you need a birthday on
Yeah,
every
so you
one
need
of
the
them.
seventh one to
Plus one.
assure that there's a repeat. But you guys had the same, you had the correct idea. That's great. That's good. All right, so that's all the discussion about probability. That's it. No more. Now I want you to focus on the function that was given to you. And it's weird because this function is not f of x equals. This function is a series of data. That's a numerical function. They're just as good as any other function. It's just a little weird. You haven't seen a lot of this type of information given to you. And besides that, even if we could do it with 0 people and 1 person, of course, 1 person, that would be done. That would be 0 also. And then 2, and then 3, 4, 5. They've done these by increments of 5 all the way through. But if you had numbers for each one of those things, it would still be discrete, which means you really shouldn't connect it with a smooth curve if it's a discrete set of data like this. Though it does look really smooth even when we count 5s. If you'll notice, the graph of this function is in the lower left corner of page 103. And it's tempting to want to connect those. Don't do it. These are discrete things. When you are graphing discrete data, discrete means countable, means you can count how many there are. When you're graphing discrete data, you do not connect them. But you can see how smooth it would be if you did. Anyway, the table 3.2 is the derivative of the function given to you in table 3.1. So the function is given to you as tabular information, so the derivative is also made up of tabular information. And remember that even if we have discrete data like you're seeing in that graph, what they're saying in that, and we'll talk about the details in just a minute here, but what they're saying is that if you would like to find the slope of the curve, and I told you not to connect it, and you shouldn't, pretend for just a moment that we did, okay? It would look something like this, okay? If we connected it, and let's say we had 2 points. I'm going to have to separate them a little bit so you can see what I'm talking about. But let's say we had this point right here, and we wanted to know what the slope of that curve was, or the slope right there at that point. Would it be a good idea to take this point and connect it with that tangent line or that secant line right there? Wouldn't that be about the same slope as that tangent line? Wouldn't it be a good approximation of the slope? Now, I realize they're not in the same place, but they have about the same slope if we look on either side of the point of interest, right? You understand that?
Yeah.
So let's take it a little bit. Let me separate it just a little bit further. Just pretend with me for a minute that let's say that this is the 5 marker. No. Yeah, it's okay. Let this be 5. That's the first 5 right there. And I know that's not true. Just go with me for a minute. I'm interested in the slope right there. Then it might be a good idea if I found the slope right here at 2.5. I'm sorry, the point at 2.5 and the point at 7.5 because the next one is 10. If I took these 2 points right here and found the slope, that'd be about the same as the slope of 5. Right? Okay. Look at what they're doing in the tabular derivative. That's section or table 3.2. What they're doing is they're saying, let's take the point 2.5 and let's find the slope. It's not quite exactly the way I described it. I did it kind of badly, but just take a look at what they're doing. They're saying, let's take the average of the x's between 5 and 0. Look at the original function. You got the first 2 points are 0, 0, and 5.027. So if you find the middle between those 2 x's, that would be 2.5. And then the slope there would be the slope between those 2 points. The slope at 2.5 would be, based on this argument right here. Does that make any sense or not? Okay, so we take the first 2 points and we find the slope between them, and we let the x value be the average of the x's, 2.5, and we let the derivative be the slope between those 2 points. That would be 0.027 minus 0 over 5 minus 0, and that's 0.0054. So the slope is practically 0 at 2.5. That's the rate at which the probability is changing for the first 5 people in the room. It's the rate at which the probability is changing. It's an estimate, but it's the best we can do when we have numerical data. So look at the next one. They let the x value for the derivative be right in between 5 and 10. That's your 7.5. So you got to be able to find your x. It's the average of the two x's you're talking about. And then to find the derivative there, or the rate at which the slope, or the rate at which the probabilities are changing, you would take 0.117 minus 0.027 over 10 minus 5, which is 5, and you get 0.0180. Did I lose you? I think I did, because you're not actually doing this. Get your calculators and do this with me and see if you can follow what it is you're supposed to do to get the derivative, what you do to the function to get the derivative here. In other words, see if you can verify that the slope between 30 and 35 is 0.0216. Find it and see if you can verify that. Between 30 and 35 people in the room, verify that the rate of change for that is about 0.0216 by actually calculating.
Oh.
Were you able to verify it?
Yeah.
Would anyone like to tell me what they calculated for the people that are listening on video? Anybody want to tell me what they actually calculated to verify it? Speak up. Go ahead, Connor.
I took 0.814, which is the probability with 35 people in a room, minus 0.706, the probability with 30 people in a room, and the difference of the y's, and then I divided that by 5, which is the difference in the x's.
Okay. And what did you call the x value in the derivative?
X value? Oh, it would have been 32.5.
Which is right between 30 and 35. Yep. So your x value for the derivative is the average of the x values you're considering. And then you use those 2 points to find the slope. You actually have to calculate it by hand. Everybody clear? Or not? That's a numerical derivative from a numerical function.
Are they as accurate as an algebraic one?
No.
Okay.
But boy, are they close, especially if your x values in the original function are very close together. This method of figuring a slope curve is darn close. Close enough for government work, as they say. Mathematicians aren't real happy with it, but if that's all they have to work with is numerical data, it's got to be good enough because it's all you've got. It's the best we can do.
They're working closer to whole numbers, and so it's more accurate.
Right. It would, yeah, if they had 0, 1, 2, 3, 4, 5, 6, 7, up to 70, and they had all those probabilities, mathematicians would be happy with that because it's closer. Still, they won't be completely happy. But most everybody else is. Okay, now, I want you to look at the slopes, analyze the slopes in table 3.2, which is the derivative. Look at the slopes, which is the y values, and tell me what you believe the derivative curve or the derivative dots, if you graph them, would look like. Look at how they're changing.
A parabola?
Well, let's see. It keeps going up, right?
Like a cosine.
It keeps going up till where? Keeps getting bigger until,
27. No, we have 22.5.
yeah, the 22.5, between 20 and 25. That's where the rate of change is growing the fastest. That's where the probability is increasing fastest. Okay, and then it starts dropping off again, right? And it gets even smaller, way smaller than we started out with a 0.0054. We got 0.0002. But look at this graph. And remember, we're analyzing slopes. Doesn't that make good sense? Look, it's really flat down here. A tangent line here would be pretty steep. A tangent line out here would be practically horizontal. Do you agree? You see what I'm saying? What I'm saying? And so it would look like what? Okay. Turn the page and see if you're right. Voila. Yep. It's like a whoosh, just like you said. Okay. Notice, please, that the x values, the x's along the x-axis and the ones that are stretched out along the x-axis of the derivative are the same x's. But in the derivative graph, you're graphing slopes. Rates of
Oh
change.
my gosh.
And rates of change were figured by slopes, which we figured by taking slopes of individual little points. Yeah?
Right.
Rates of change in the probabilities. Okay, enough discussion on that. Last thing would be example 6. We've actually already done example 6, and you've actually already been tested on it, which isn't really fair, but we've had the discussion. You've been tested on it already on a test.
What?
And now they're finally introducing how to do it, but I told you how to do it when you needed it, so don't panic. Here we go.
Okay, I'll redo that.
One-sided derivatives. If you have a function that you're only interested in from x equals a to x equals b and that's it, then at a and at b you have only one piece of curve coming into it. And so if you want to know what the slope is at b, then you analyze the limit as x approaches b from the left. Because that's all you have. So one-sided limits are okay if you're testing the end of an interval. That's all we're saying.
Between that and just testing that point without the closed interval.
If you don't have an actual function, but all you have is a curve, then you're gonna have to draw a line at that point and not know what's happening on the other side, that's all. It's not a big deal, don't make too much out of it. I'm saying, if you wanna figure the slope at the end of an interval, you may use, it's okay to use only that piece of graph that you can see to find it, okay? All right, so example 6, you've already done this, it's a piecewise function. We have a parabola as long as x is less than 0. The parent curve for parabolas. And you have the line 2x for x's that are greater than 0. Can you see that the graph on the left seems reasonable for this? Now it says, verify the existence of the left-hand derivative. Well, just a minute. It says, show the following function has left-hand and right-hand derivatives at x equals 0, but no derivative there. The left-hand derivative would be where you analyze it coming in from the left, which would mean the parabola, right? And the derivative of the parabola at 0, by using the difference quotient, is 0. Besides that, graphically speaking, the horizontal line there would, for the parabola, would have to be flat, the tangent curve, okay? The right hand would be getting on this piecewise function and coming in from the right towards 0. And that slope is always 2. And since the slope from the left and the slope from the right at 0 are not the same for this function, there can be no derivative there. Does that mean it's not continuous? It's continuous. The limit is the same. Remember, limits at that point, if they are the same, make it continuous there. And the limit from the left and the limit from the right is 0. But the slope from the left and the slope from the right are not the same, which means there's no derivative there. The derivative is undefined at 0.
The fact that it teaches this twice with different words is just more confusing than teaching it to us once.
With the same thing.
You understand the difference between limits and slopes?
Yeah.
Limits is asking continuity. Slopes is asking derivative.
Yes.
Yes? Okay. All right. We will discuss that more in the next section, this kind of a deal, but they have to have the same slope from the left and the right for there to be a derivative that exists there, and there isn't one at 0 on this one. Yes?
Can you find a graph of a function derivative? Are we going to do that?
We did that. We did that.
You did?
We already did, yeah. Were you not here Thursday?
I was, but.
The derivative graph is like this, and so is the.
Right here. This is the derivative.
Oh, yeah, I remember now. Oh, this is the derivative. Okay.
And had these two stupid.
Okay.
We'll get ones that are tougher than that. I mean, that's usually first day, but yes, you can.
Okay.
Yeah, okay. As a matter of fact, that is the entire subject around integral calculus, which will be the last half of this course,
Oh, yeah.
is recovering functions
That's where
from
you
their
have to
derivatives.
remember.
So we'll get there. We'll get there. Anyway, that's the end of section 3.1. Good luck. Call me if you need help. Bye.